Now, let us see what simplification can be made. So, first is n 32 is nothing but minus of n 23, I have told you, because they are the reactions, right. So, n 32, that means body 3 applied on body 2 is nothing but the negative of 2 3. So, that is the expression that makes it cancel out. Then the next one F 32 is also minus F 23. So, they also cancel out. Okay. Next R 2 F 32 here is nothing but minus of R 2 F 23. So, I have R 2 cross F 23 here. So, these two will cancel out. Okay. Then the next one is minus D 3 F 23 and D 3 F 23, they will also cancel out. Okay. So, finally, what remains is as follows. So, W 2 C tilde n 03 as it appearing there. So, n 03 here, n 03 here, then you have n 12, you have n 12, then you have minus D 2 F 12, you have minus D 2 F 12, at the below you have F 12, you have F 12, you have below F 03, F 03. What are the other terms remaining? R 3 F 03. So, R 3 F 03, and then this guy will give rise to R 2 F 03. So, this is R 2 F 03, and then this guy will give D 3 F 03. So, D 3 F 03. Doing this kind of analytical symbolic manner will lead to many physical interpretation. Even in this case we have interpretation. Let us see what it is. R 2 plus D 3 plus R 3. So, R 2 is here, D 3 is here and R 3 is here. So, what is the final vector in that case? Final vector from the mass center of the second body to the tip. So, which I am indicated with a P 2 vector. Okay. So, now I have the final expression for W 2 C is this much is replaced by P 2. If you proceed now the calculation as we have seen in the previous slide, that W 1 C tilde, if I give this name, the whole term here, if I give this as a small W 1 C tilde, then I can calculate that expression in a similar manner to the above expression as n 03, n 01. Now, P 1 from the mass center of the first body to the tip. So, P 1 cross 03 minus D 1 cross F 0 blah blah blah. Now, interesting point to note here is that F 23, F 12, which are the reactions from the interlink interactions which are getting coupled. So, which are getting coupled, they are getting cancelling out, which we have seen in case of our serial link system as well. Okay. So, now the last part is N D transpose W C tilde. So, this will be P 1 transpose, P 2 transpose, P 3 transpose, whereas the meaning of P 1 is E 1 cross D 1. So, I have written for all 1, 2, 3. So, the first one I am showing it in detail, tau 1 C, ultimately it will be a scalar quantity, which is P 1 transpose W 1 C tilde. So, I have written from my previous slide what is W 1 C tilde and then this expression here. So, the first operation I am doing it E 1 transpose this expression. So, which is appearing here. Then the next one is here. So, which I am doing it there. Now, interesting thing to note here is E 1 transpose n 03, it will be 0 because E 1 transpose is a vector quantity which is perpendicular to this plane of motion. Okay. Now, n 03, the way I have defined n 03. So, for the 4 bar linkage, so here at this junction I had n 03. So, for such a planar system n 03 has a component about x this directions or this direction, okay. But E 1 is perpendicular to both of them. So, E 1 transpose n 03 will obviously be 0 because E 1 is the axis perpendicular to the plane of the motion and N03 are the reaction components about x and about y, okay, because about z there cannot be any reaction because it is allowed to move. So, with that understanding we know that E1 transpose N03 will be 0, then N01 will be 0. What will remain? Something from here, something from here, and of course, from those. So, if you now do the simplification, now this will look like E1 transpose rho 1 cross F03. What is rho 1? It is like a P1 only, but instead of the vector from the mass center to the tip, it is from the joint to the tip. So, this is the vector rho 1. Okay. And if you do the simplification here, this is another property from vector algebra, that A transpose B cross C is nothing but A cross B transpose C. This is from the vector triple product, this property is valid. Okay. So, this property I am using it, that E1 transpose rho 1 cross F03 is equal to E1, because F03 is my unknown quantity and I wanted to separate it out, because I need to do something with it, and other quantities here, these are the geometric quantities. So, I know from a given system. So, in this expression you have E1 transpose rho 1, E1 cross rho 1 transpose F03, and now similarly if you find out the other two component of the constant, tau 2 C will be this and tau 3 C will be this. So, rho 2 will be from here to here, and then rho 3 will be from there to there. Okay. So, I go back to my the expression which I started with. So, I theta double dot plus C theta dot, I told you this is a known quantity, means I can compute it for given parameter. I give it a name for simplification purposes, tau star. So, this is a known quantity. Tau E, the external component, will be only tau 1 0 0. As I told you, the external torque is applied only on the first joint, because typically you will put a motor on it, no, to drive it, and the second term tau C is nothing but J transpose F03, and J I have calculated in my previous slide, that E1 cross rho 1, E2 cross rho 2, and E3 cross rho 3 is nothing but the A3. And now for a 3-link system, it is a simple matter to find out what is the Jacobian matrix for this system, which I will briefly indicate on my paper here. So, we know this point, say P is nothing but A1, A2 and A3. So, P is equal to A1 plus A2 plus A3. In classical Jacobian definition, I know the P dot will be A1 dot plus A2 dot plus A3 dot. Okay. And if you do this all these derivations, you can find out that this expression writing in terms of theta 1, theta 2, theta 3 dot will be nothing but E1 cross rho 1, E2 cross rho 2 and E3 cross rho, little clumsy here, but I can calculate for you A1 sin 1 minus A2 sin 1 2. Here I have tau E, the 3 equations, J transpose F03. So, can I bring it down to one equation? The answer is yes. So, can we bring to 1? Yes. How? Now, that is a very simple matter. What we have done is here theta, say theta dot, we have taken all joint rates, but we know for the 4-bar linkage all joint rates are not independent. Okay. So, what we can do, we can use our earlier constraint equation A1 dot A2 dot plus A3 dot is equal to 0, that we have written as j theta 1 dot theta 2 dot theta 3 dot is equal to 0. You can partition this j as j 1 and j 2, where you partition in the following manner. So, j 1 theta 1 dot is equal to plus j 2 theta 2 dot is equal to 0. So, theta 2 dot contains two dependent one, because we know this has 1 degree of freedom. If I presume the theta 1 dot is my independent quantity, then I can calculate my dependent quantities as j 2 inverse j 1 theta 1 dot with a minus sign here, and then what I can do is I can write this guy as 1 and j 2 inverse j 1 minus. I rewrite this thing in the next slide. So, I write theta 1 dot theta 2 dot theta 3 dot as 1 minus j 2 inverse j 1. Okay. So, now if I have the following equation of motion, and in the similar manner to what we have started with Newton-Euler equations to Euler-Lagrange equation, here Newton-Euler equation to some reduced form we brought it, but now if we give this guy a name, so j prime, if you pre-multiply it by j prime transpose, pre-multiplied by j prime transpose. So, one can now show that j prime transpose into tau c is equal to 0. So, it can be shown. So, my final equation of motion will look like, so this will become a scalar quantity I theta 1 double dot is equal to tau, but this I will look a very complex expression. So far I have not seen any textbook which is reproducing the expression of it. So, this will also there is an inversion calculation is required, right. So, doing it all this by hand will be relatively tedious process. Okay. So, can I do something in between now? So, what we started with 9 by 9, then 3 by 3, and then I know how to do it to 1 also, right. So, can I do something in between? Answer is again yes, and that brings down to another advantage which I will mention after I explain this thing. So, what we call is a subsystem recursive method. Okay. What it is? So, now what we do is instead of opening at the fourth joint, so in the 3 link case I have opened it here, but I say no, do not open it there, you open it here 2. Okay. You may ask another question little later that why not 3, that I will answer little later, but for the time being let us say I do cut it at 2. So, I cut it at 2 here. So, now I get 2 subsystem. Okay. Instead of 1 3 link system I get a 2 subsystem, and both are actually a serial system. Okay. If you consider all together, both together, it is like a tree type system. So, this is like a stem, this is one branch and this is another branch, but for us it is a 2 serial chain system. Now, for the first serial chain system which is subsystem 1, I have learned how to calculate how to derive the equation of motion. I write it in a very standard form. Only thing is that I know that this constraint will not be 0. So, I keep it as it is. So, this gives rise to one equation, but how many unknowns? 3 unknowns, because tau 1 is the applied torque here and F 2 1 has 2 component, which I have for some reason I have put it also as a lambda. So, lambda x lambda y. So, 3 unknowns, but one equation I cannot solve. So, I take the help of the other subsystem. The other subsystem will give rise to 2 equations of motion, what you call is a 2 constraint equation of motion, and how many unknowns? F 1 2, 2 unknown. This I can solve, which means given the motion I can calculate what is lambda x and lambda y. So, it is a 2 word system, I can solve it. So, I solve it. After I solve it, and how you solve it, that steps, there is no torque applied here for the 4 bar linkage. So, they are 0 0 here. So, J 2 transpose lambda, J 2 is a 2 by 2. So, given this quantity I can invert it, I can calculate lambda. This lambda now you substitute it here, then this becomes a known quantity, left hand side is already known. So, I can calculate. So, this is called subsystem recursive. So, I solve second subsystem first, followed by second subsystem. So, what are the advantages for this one now? So, one thing is I can do system recursion, right. In fact, so now I can solve it, which is nothing but equivalent to the 3 link system. So, if you have to cut other than this place, the best way to cut is here. By observation you can check that which way I can introduce the subsystem, okay, and then cut it. If you are not worried about benefit of one dimension, then you really do not worry. But as I told you, recursive methods are mainly applicable for larger dimensional problem. Okay, so, here I have the results for the 4 bar linkage, but I will show you this one using one MATLAB based algorithm which is available through net also. So, this is the website as you can see it, and then I will run it for you, this MATLAB program. So, this MATLAB program is actually meant for the tree type system or open loop system, and then a small module has been added to take care of the constraints, the J transpose lambda calculation, and after that it is using the same stuff. Okay, so, this is the animation you see for the 4 bar linkage, and here you have the driving torque. This is the driving torque. As in my slide I have shown you, there are validations using Atom software, and then this is the input, the joint motion, and then it has showed the reactions also. So, these are the reactions actually. Let us close it. Oh, where did it go? Okay. Joint rates, animation. So, I think it has just jumped very quickly. I will run it and then I will show you again. Okay. I think it has closed automatically. The reactions are also calculated. Okay. Now, the same thing with a little modification, if you wanted to do the forward dynamics, which I will explain in the next class. So, today let us try to understand up to the inverse dynamics. So, we have showed you 3 different ways. One way is to 9 by 9, another is 3 by 3 and 2 by 2. In fact, I have mentioned about the 4th way also, which will give you independent set of equation of motion, which will have complex. So, there is always a trade off between complexity versus the formulation simplicity. So, when you have a simpler system like 9 by 9, you know it is very easy to understand. 3 by 3 was little complex to understand, 2 by 2 is almost same, but numerically there are some issues which we will not discuss in this course. However, if you have one equation of motion, the expression will be very complex. So, with this I stop. If you have quick questions, I will take it.
Degrees of freedom more than this 4, more number of links if you have, how do you decide where to cut? For this it was obvious 2 only we could do.
Right.
If it is more than 3 links only.
It is not very straightforward, but there are some concepts called cumulative degree of freedom. You wherever you cut, you count from all sides that what is the total degrees of freedom coming. So, wherever the degrees of freedom will be minimum. For example, here I had 3 and 0, right, and then 2 and 1. So, this is the best combination you can have it, right. You cannot have 1 1 or something, 2 and 1. So, this is the best combination you have. But then where to cut, there is no straightforward analytical tools to decide it. So, this has to go little bit with the observation, and you have to do it. Sometime it may not be possible either. So, then what you have, suppose you may have 5 subsystems, then you have to see which 2 to combine. So, maybe 2 of them combining you will get a certain set of determined system of equation, right. After solving 2, then you can come to the other. So, that is also possible. Okay. So, let us stop here and we will see on 26 the Friday, but I would expect that you guys browse through the derivations, because what has been done is higher dimensional algebra has been done. So, if you do little bit of yourself, it will be very beneficial for you to understand the concepts. Thank you.